Hey IB Physics students, welcome back to my channel where we are gearing up to ACO 2025 exams. Today, I'm diving into question 2 from the 2021 paper 2, solving it step by step and breaking down the key concepts behind it. Whether you are struggling with the theory or just need some exam practice, this is for you. So smash that subscribe button and let's get started. Question 2, Part A. State what is meant by the internal energy of an ideal gas. So when we talk about ideal gases, we mean gases in which the particles or the atoms, they don't have any potential energy. They are free to move. The only time they interact is when they collide. If they don't have anything to do with one another, meaning there is no potential energy, all the energy must come from kinetic energy. So we should say the internal energy of an ideal gas is exclusively due to kinetic energy. So let's write that down. Internal energy is the total kinetic energy of gas. Let's move on to the second part of the problem. A quantity of 0.24 moles of an ideal gas of constant volume 0.20 meter cubes is kept at a temperature of 300 Kelvin. Calculate the pressure of the gas. So what are we given here? We know the volume. So volume is given to us, V equals 0.20. We're given the number of moles. So that's N for us. N equals 0.24. The temperature is given to us. It is 300 Kelvin. And we are supposed to find the pressure. So how do we do this? Well, if we go to our data booklet, we see this equation, PV equals nRT, also known as the ideal gas equation. So let's use that. So I can write PV, pressure times volume, equals the number of moles, the ideal gas constant R times T. The value of R you'll find again in your data sheet. So let's go back to our data booklet. You'll find the value of R right at the top. So if you scroll up, you'll find the R value is given here. R is the gas constant. It has a value of 8.31 joules per Kelvin per mole. So we want to find the pressure. So let's rearrange this equation. P is nRT over V. And now I can substitute all the values. N goes here, V goes here, T goes here, and the value of R we can look up from the data sheet. Let's do that. We have N as 0.24, R is 8.31, the temperature is 300 Kelvin, and the volume is 0.20. So let's plug this in, and this gives us a value of about 3.0 into 10 to the 3. The unit of pressure is Pascal, also known as Newton per meter. Alright, that's good. We found the pressure of the gas. Let's move to the next part of the problem. The temperature of the gas is increased to 500 Kelvin. Sketch on the axis a graph showing the variation with temperature of the pressure of the gas during this change. Well, I can take this equation once again and change the temperature from 300 to 500 Kelvin. Let's do that. So once again, the pressure would be P times the volume is given 0.20 equals the number of moles is 0.24, gas constant is 8.31, and the temperature is 500. That means the pressure would be 5.0 into 10 to the 3 pascals. So the initial pressure is 3 kilopascals that we found here. And after increasing the temperature, the pressure goes to 5 kilopascals. Alright, so let's draw those two data points on this graph. When temperature is 300, the pressure is 3 kilopascals. That means we are looking at a data point over here. When the temperature is 500 Kelvin, the pressure is 5 kilopascals. That is a point over here. So these are the two data points we have. We also know that in this equation, N is a constant, R is a constant, V is a constant. That means P is directly proportional to T. This means that the graph between P and T must be a straight line. That means we just have to connect these 2 points, because the relationship between pressure and temperature is a straight line. Alright? It could not be something like this, because that's not a direct relationship. And that solves this part of the problem. Let's move on to the next one. A container is filled with 1 mole of helium and 1 mole of neon. Compare the average kinetic energy of helium atoms to that of neon atoms. So we have a container and it contains 2 types of gases. We have helium atoms and we have neon atoms. But since the 2 gases are present in the same vessel, both of them have the same temperature. So temperature of helium is the same as the temperature of neon. If you look at your data sheet, you'll see an equation that connects kinetic energy with temperature. That equation is present here. This is the equation that relates the total kinetic energy with temperature. From this equation, we realize that no matter the type of gas we have, if you have the same temperature, you're going to have the same internal energy. Since an ideal gas, the internal energy is just kinetic energy. It means if you have the same temperature, you're going to have the same kinetic energy. So if you go back to our question, the temperature of helium and the temperature of neon, it's the same. That means the kinetic energies of helium and neon, they're going to be the same. And that's it. The average kinetic energy of helium atoms is the same as that of neon atoms. I hope you found this video helpful. I also teach one-on-one. The link will be in the comments below. I'll see you in the next part of this problem. Till then, happy learning.